So I will talk about parallel computing with Python, right? So in the previous day, you have seen some features from Python running in parallel mode using different cores. So I will cover, for instance, different mechanisms of parallelization with Python and how to implement a parallel algorithm in a simple Python code. I would say this part of the course is advanced depending on your previous knowledge on the parallelization, right? And I will cover just a simple program. I will not go into the details because in general, it's not straightforward to implement a parallel algorithm in your current Python workflow. And also, I will show you how to deploy threads or workers in your HPC centers. So before we start, we need to do some installations. And in general, this is the way how we work with more complex workflows in Python because we have already some modules for Python available, but in, in general, I would say we need to install the dependencies, yes. And previously, in the previous lectures, we have seen how to create an environment, right? And how to do our own installations. So I cover here how to do that in the different centers. And here you can see HPC2N, and I will cover NSC, tetralit today. Yeah. So this is part of the workflow, as I said previously. Yes, when working with Python in parallel mode. So here, for instance, in tetralit, I need to load, uh, build the environment, right, module, and I choose this one, yes, because it contains the CUDA as well. So first of all, I load the module. Interesting, it's taking some time. And then I create my own environment and source the environment to activate it. Oh. So once it is ready, right, you saw that previously how to install the packages in your own environment. We need to install MPI4Py, Number, and also I load this version of Julia. Julia is a programming language, right, that doesn't need to be compiled. And it is useful to illustrate the connection of Python with other languages. So Python has a very good interface for connecting with other languages. It can connect, for instance, with the C, Fortran, Julia, in this case, MATLAB. This is just an illustration on how Python can connect with other languages. So depending on the needs, maybe you have already some code written in another language and you want to use that in your own workflow. So finally, it is loaded. I don't know why it took some time. So then I can create the environment with Python -n and VM, and I will put it in my current directory, right? So I did it previously, and because of that, I won't execute that right now. And then I can source the environment. And then I start with the installations. PIP install MPI for Pi, right? So notice that I am using an environment because sometimes it is not easy to get all the packages that we want with the modules that are installed in the HPC center. That's why I customize that in this environment, and in this case for Tetralit, it should work, right? So then I can install a MPI for Pi. And in my case, it shouldn't take a long time because I already did installation, so it is repeating the operation, right? But in your case, it can take some time, especially for large packages. So I can do the same for Numba. And Numba, I saw that previously with Rebecca. And also, I can load Julia. And again, this is to show you how you can connect a Python with other languages. And then I can install this connector between Julia and Python, which is called Julia call. Yes. And here I need to do another step, but inside Julia. So here I open Julia. This is the Julia environment, right? And here I do an installation. I press the bracket, the right bracket, and then this led me to the package mode, and I can do this Python call, right? And the package that takes time is a PyTorch, right? And it will take you some minutes. So PyTorch is necessary for this package that I included, which is called HIT. And this is a very interesting and novel package that can help you to parallelize some machine learning workflows. So after this, I press a backspace and then exit the Julia session. So now we are ready to use Python and Julia. And if you want to use, for instance, a C or Fortran, so the connector would be different, right? So here we can install a PyTorch. And it takes some time, but as I said before, I already installed it, and it is not doing anything at this point. So PyTorch is needed for the heat package. Also, I already did installation, and there is also another package that is called PyOMP. So everything is there. So we are ready to go. So So we can start with the parallel programming. So here I wrote a definition of parallel programming. I wrote that this is the science and art of writing code that executes tasks on different computing units, cores. So we have seen this word previously during the course, the cores, right? Which are the units that execute the computations. So in the past, the computers were shipped with a single core per a central processing unit, also called CPU. And therefore, when we talk about a core and CPU, this was a synonym, but currently there can be several cores in a CPU. For instance, in my Mac, right? I have several cores. If you open the activity manager, you can see the different cores that are being used in your machine. And this is in my case, it has up to 8 cores, right? So, and we can distinguish two main architectures, right? In novel computers. So we can see that there is a shared memory architecture and also a distributed memory. So the main thing in the shared memory is that the different cores, yes, can share some memory address space. And the advantage of this is the bandwidth because the cores have access to this memory in a very fast manner, right? So this is the main advantage. We have also the distributed memory where the cores do not share memory among them, but they can get the data from the other cores by sending messages and receiving messages. And this is a different mechanism, yes, for parallelizing the code. So as you can see here, the architectures are not that simple as simply shared or distributed memory, but there can be a combination. For instance, here, there are some cores that work in the shared memory architecture, but also they can use the distributed memory by sending and receiving messages. So the architectures now are more complex than this. And this could be a combination of different types of architectures. So this is how a standard node in Kemnekaise looks like, right? So we have in some nodes up to 28 cores, and they can share some memory. In this case, 64 gigabytes per socket. And in a whole node, when there are two sockets, we can have up to 128 gigabytes, yes, that the cores can share. And this type of parallelization with shared memory can be very efficient on a single node, right? So, so here I put this figure to illustrate why parallel programming is needed. So if you write your code in Python, right, and you don't include any parallelization mechanism, then you will be using a single core as it is depicted here. And I show you that in my case, with activity monitor in my laptop, I have 8 cores, right? So if I don't include anything, any parallelization mechanism in my Python code, I will be using one, but I can also use more than one core if I include some package or some strategy in my Python code so that I can use even more cores, right? But in our HPC centers, we don't have only 8 cores, but we have plenty of them, right? So you can use here some shared memory for some programs, but also we can use distributed memory because the programs can send and receive messages across all of these nodes and cores. So you can scale your program in different ways. And the goal or the idea would be to use most of the cores available on the computing node. But in reality, that is a very hard thing to do in current codes, right? There are some codes that can do that well, but it's not general. So here I show you a situation that can happen in the course in the HPC centers, and you have seen previously that you can request the number of cores and the number of nodes that you need. Yes, and sometimes we can request more resources that we need, or even less resources than we need. So in this example, I show you an illustration of what could happen. For instance, if we request more resources than needed, right? And then the computers are yours idle, right? And only one a single core is doing the processing. So we have several tools in our centers and how to, that allow you to monitor the resources that you are using. And for instance, at HPC2N, we have a tool called job usage. You can see here the description of this tool. It's a graphical tool that can be opened in your local browser. At other centers, this tool is not present at the moment. So if the new machine arranges, most likely it could be present, yes. But if it is not available in your center and you don't have access to a graphical tool, then what you can do is to use an interactive session, right? And then here the top or htop command is available, and this will give you the information of the resources usage in a text-based form, right? So this can help you, for instance, in case you request less resources than the program needs, then you will see that the resources are exceeded, right? Or less, or even more resources that you are needing. So I will show you the idea on how to parallelize a Python code, right? With a simple demo. And this is a language agnostic code, right? That evaluates a loop starting from 1 to 4, and then we wait for 1 second and end the loop. So this wait 1 second represents a function that can be very complex, but at this point, I don't want to introduce a complex code, right, that could affect the understanding of this loop. And that's why I just put a simple wait function for 1 second. So imagine that you write this code, and these type of loops are very common in scientific code, where we want to perform several iterations and repeat the task. So this could be also more complex because there could be other for loops that are nested, yes, in the inner part of this code, right? So these for loops can be very heavy. So as it is, right, the code will run on a serial core or a serial CPU, as it is here, right? And then because there are 4 iterations, we will have 4 pieces of work of 1 second, right? So in total, this code will take 4 seconds. So but imagine that we somehow parallelize this for loop because the tasks are independent of each other, right? So the iteration 1 doesn't depend on the iteration 2, and so on, right? So the iterations are independent. We can parallelize that in some manner that I will show you. And then in this case, we can execute this loop, each iteration on a single core, right? And because of that, the total time or the ideal time will be divided by 4, yes, and so the total time will be 1/4 of the serial code in the ideal case. However, the ideal case is in general not achieved, right? And it's just an upper bound of what you can get to parallelizing the code. So how to parallelize this code in Python and how to write that? For the wait function, we can use a function called sleep.py. Yes, sleep is the sleep function in Python, and call that some number of times. So for the parallelization, we can use the multiprocessing module that is included in the base library of Python. So you don't need to make any installation, right? Any further installation with PIP, for instance. So it's included already. So here we start the Python code, and we import also the multiprocessing module. So we define the number of iterations and also the number of processes. So here, notice that the number of iterations is equal to the number of processes, yes? So that each process or core takes one of the iterations. So we can write the serial example. This is here, is a simple function in serial mode. And you can see that iterates in the range of 4, and then it sleeps for 1 second only. So this is the serial function. If you execute this, it will run on a single core. So but you can now parallelize this function with multiprocessing. And here we define a new function called credit, which accepts the number of iterations, the number of processes, and the process index. Yeah? So the workload is the total number of iterations divided by the number of processes. So we define a beginning and an ending for the iterations that each process will execute, right? So you can check that with a pencil and paper, and you will see that the range matches one single iteration per process. And here you can see that the sleep function is for 1 second as well. So then we start the main function and we time the serial function, right? And also here we start the timing of the parallel code. So here we can use a shared array, yes, for collecting the processes. And here there is a way to start the multiprocessing, right? Using the sleep threaded function. And here we write the arguments that the sleep threaded function needs. Yes, you can see distinguish what are the arguments in this case. Then we start the processes, and then we need to wait for the processes and join them. And finally, we report the time for this function. Here there is a way to run it on Kebnekaise, but we are using now a tetralib, yes, and we can use 4 processes to run the script, and I can do this. You go to this button here, we can copy, and then here we create a file called sleep.py. So then, because this is a short job, right? Instead of writing a batch script, we can run that directly with the srun command and using the same inputs, yes, that you will write in the batch script. We can use, for instance, srun, the project, yes, the project name, 1 task, yes, I will use 4 cores. Then the time is just 10 minutes, Python, and here I will write the name of the program, which is sleep.py. So I run this with srun because it's a short job, right? But otherwise, for longer jobs, or if you want to keep track of the job, then you can use your batch script. Yes. Here you see that the time spent in serial mode is 4 seconds as expected, and in the time in parallel mode is 1.1 second, right? So notice here that, as I mentioned before, the ideal value, which will be 1 second only, is almost never achieved, I would say, because calling the parallel libraries and also doing the settings, yes, in doing the settings, Python incurs in an extra overhead, right? And because of that, the ideal value of 1 second in this case is in practice not achieved. So we also need to take care of this, right? Because if we want to parallelize something that is very, very fast, in general, we won't see any performance gain. So the task that is being parallelized needs to be heavy enough to compensate the parallelization mechanism that we are including in addition to the standard Python workflow. Also, regarding the underusing or overusing the resources, notice here that it is just right, yes, the amount of resources that are used, which is 4 processes, right? and then 4 iterations. So, but if we use, for instance, 2 processes and 4 iterations, right? Then we could obtain more benefit, right? If we use 2 additional processes. So in this case, would be underusing some resources. Also, if we use more processes here than iterations, then we will be over allocating the resources. So can we always parallelize an algorithm? So in general, this is not the case. So there are some algorithms that are not parallelizable at the first site, or even they cannot be parallelized. And here I show you an example that of a serial algorithm that is not straightforward to parallelize. So let's take this example here. We have a for loop, yes, as we saw previously, and then we do this iteration. The element of the array I is the element of the array I minus 1, and we sum the I value here. So let's take 6 elements only and only 2 processes, right? And then one process takes the elements 0, 1, and 2, and the second takes the elements 3, 4, and 5. So if we try to parallelize this, right, we will see that the iteration of I that depends on the I minus 1 will cause a conflict, yes, because the element A3 will depend on A2, and this is owned by the process 1 that is modifying that most likely, yes, at the time that I3 is being accessed, right? And because of that, because of this data dependency, we cannot parallelize this algorithm just by including the multiprocessing mechanism that I mentioned before. So, but if we convert our initial algorithm to one algorithm that is parallelizable, then we can perform this task. So how to do this? So we change our mindset in this case, yes, and we rewrite the algorithm that produces exactly the same but here, as you can see, iteration only that it can with multiprocessing or any other type of parallelization. So
sorry, you
yes.
went away for a while. Could you do that
Okay,
again?
so
The sound went bad.
which part? Sorry.
Just the last for loop.
Oh, this one?
No, the second one that you just talked about. No, further down. The one
This
that
one.
just last one. Yes.
Okay. Okay. Yes. As I mentioned, we can rewrite our serial algorithm, right? So that is suitable for parallelization. For instance, in this case, I make the element I independent or of other elements, right? So as you can see here, and this algorithm is more suitable for parallelization. And that's a very interesting thing when we try to parallelize our serial code in Python, yes, because it is not just to put the parallelization directives in our serial code, and then we expect that the code will run in parallel mode, right? Because we need to take care of data dependencies and notice that there are several things that we take for granted in serial mode, right? But if we go to the parallel mode, they need to be rephrased or refactored, right? So that it's suitable for parallelization. Another thing that can be that can happen, for instance, imagine that you have a large database, yes, and then you are running a serial algorithm with a for loop, right? And then you notice that it works well, it's producing good results. Then you want to go for a parallelization strategy. You don't pay attention to the size of the database, and then you replicate the data across different cores, right? So this could be an issue because in that case you will be over exceeding the memory that you requested in your bash script, right? What can do in that case, for instance, is that instead of replicating the whole database, one can divide the database into chunks, right? So that each process takes care of one chunk, and we don't need to replicate the whole data. So these are a couple of things that we take for granted, right? Data dependencies, the size of the data when we are in serial mode, but when we go to parallel mode, we need to take care of them. So here I show you a second example, and this is a more elaborated example. This is an integration, yes. And here we're integrating this function because we know the analytic solution, we know how to compare with the results. Yes. So how can we do this implementation? So we notice here that we have two directions, and the way to do the integration is by creating a grid in both X and Y directions, and then we divide the axis into endings, right? So here there is a naive implementation, I would say, in the serial mode without any optimization, yes? And this is how I would write this quickly. So here we define the grid size in both directions, X and Y. And here we define a cumulative variable, my sum, which will collect the values of the function at the different grid points. And here we see a more elaborated for loop, because in this case, the for loops are nested for the I and J directions. Here I write the X value, which is the grid size times I plus 0.5. So if you check this with pen and paper, you will see that you are in the middle of each bin value, yes? And also I do the same for the y-axis, and here I collect the function value at that point, yeah? And finally, I report the integral, which is the bin size squared times my sum. And here I report the serial implementation and also the timing for this serial implementation. So you can see here that on the terminal we can write Python, the name of the script, and so on, and execute that. But because this is a task that will require in the future examples some course, so it's better not to run that directly, but instead we will use srun, and then we will be running that in the computing nodes, right? So how to do this? I will do something similar to what I did before. And I already have this integration to the serial. As you can see here, I already copied and pasted the file in my directory, and it's available. It's exactly the same that I explained. And here I can execute that with srun. And notice that here I am not using the output and error flags, right? So you can also use that, and they will write the output files, and then you can check the timing there. So these are the flags that you can use, right? Here they will write the output and also the error if the program has errors, and then here you can check in the output file the timings. But I am not using that, and because of that, the outputs are written on the screen. So you can see here the time that it took is about 20 seconds, and this is serial mode and NAISS implementation. And I call it NAISS because I didn't make any attempt, yes, to make it efficient. Okay, so now we know that the output of the serial code is correct, yes, because it's close to 0, as you can see here. So otherwise, if we are still struggling with the serial code and it is not producing yet the results, right? So then we should continue with the serial code until it gets it gives us a correct output. Why is that? It is because it is easier to debug the code in serial mode, right? Rather than going to the parallel mode and trying to discover the errors there, right? So we will have also errors in parallel mode, but we know that we have working with a program that is producing the correct results. So okay, so before we go to the parallel mode, because you have seen that there is a terminology, there are new concepts that we will need to learn when going to the parallel mode, right? Then, before moving to that step, we can try to do some serial optimizations and see if we can stay with the serial code, right, without including any parallelization, and achieve some performance that is optimal for us, and we can avoid, yes, going to the parallelization project. So we saw this previously in a previous section. So there is a module called NUMBA that can assist us to obtain a compiled quality function, yes, with minimal effort. And this can be achieved through the NUMBA decorators. And an example is here, it's an NGIT decorator. So going back to my previous example for the integration to D. So here I show you exactly the same function as before, right? I didn't make any modification. This is the same function as before. But here notice that I am calling a NUMBA, yes, and importing the NGIT decorator. So how can I run this function? So I can run it here with NGIT, yes. I put the decorator here at this step, and then here is the argument of the function. And I am taking the time for this function and reporting the time. So I already did this step. Let me see. So NUMBA is here. And as it was mentioned yesterday when we saw NUMBA, so the first time that NUMBA gets the function is doing some additional optimizations, right? And because of that, the initial or the first time that the function is called, right, it produces a relatively large, longer time. But we can also execute that a second time and see how the performance is modified. So we can run the code. And notice here that the code is serial. And in this case, I was requesting for 4, right? 4 cores. This was my mistake, sorry. You see that here I am using more cores, yes, or allocating more cores than what my job needs, right? Because it's serial mode, it's 1 core only. So this was my mistake. Okay, I can allocate this. And you can see here that the first time that NUMBA was called and the NUMBA decorator was used, the time was 9.7 seconds, and the second time is much lower, it's 2 seconds. So we reduce the initial time of 20 seconds to 2 seconds, right? Just by including the decorator. So, but as you can see here, yes, I had a well-structured function, yes, and I applied the decorator. So this is a good way to go with NGIT, yes. So instead of having a sparse code, right? So it's a good idea to enclose the important features and maybe the expensive features into functions, and then use NGIT for these functions, right? and try to see if you get some speed up. So coded in functions with functions that include blocks of code is a good practice, I would say, instead of writing a very long code and then engine won't have any effect. Yeah. So this is a very specific function, and because of that, engine works very well in this case. So yes, we can also interface Python with other languages. I only include a few of them. Yes, and you can also search for other connectors. For instance, C and Python. That's possible. Here I mentioned the Fortran because Fortran is a program that has already some libraries, right? It's very complete in this sense and very old. So here I wrote a function, the same as before, because I knew, yes, that the integration part is the most expensive one. And because of that, I wrote the function important, right? Yes, here you can see how the code looks like. And then here we need to compile this function because this is Fortran code. And the way to compile that is by using this command here. So once you load the Numba module on Tetralit or on your machine, then you will have this command Fortran to Py, yes, available on the terminal, and then it will try to compile the function, yeah, and generate the so-called API, which you can see here. So basically, it's compiling the code, right? And once you do this, you will see that the API, the my function, is there. And this is the API that we will use, yes? So how to call the Fortran code? We use this caller, right? And here we import my function. This is the way to import the API that we generated. We define a grid size as previously, and then we copy this and create a file, vim called Fortran code.py. So I already copied and pasted this function, as you can see here. So then we execute our code as before with srun. We are still with one core, right, as it is here. But here the code is called Fortran code.py. So why are we doing this with C or Fortran or Julia? Because they are much faster languages than pure Python, right? So if you know how to code in any of these languages, then there is a possibility to connect Python with these other languages. And as you can see here, the time is reduced to 1.2 seconds. Yeah? But notice that if you are still developing the Fortran code, yes, then we will need to recompile the code with this command here every time that we modify the function .f90. And that's a shortcoming of calling a C or Fortran, right? Because we need to recompile the code. So because of that, I included Julia, yes, just because of that. It's another language, right? but it's a language that don't need to be compiled, right? And it's also or can also be interfaced with Python. So here I wrote the code in Julia. You can see here the code, basically the same integration part, which is expensive, yes. And here is the way to call the Julia code. And because in Tetralib, we are using the version 1.94.4, so I will use this code here, yes. And I will call the code call Julia code.py. So notice that I am not compiling the Julia function as I did in Python, or one should do in C. I am just calling the script, and this saves of time when compiling the code. So then how to run the code, the same as previously, is run, call, but in this case, Julia. So you can see that the time is about 1.8 seconds. Yes. It looks, yes, like the real time was longer. Yes. And this is because here, just at the very beginning, Python and Julia needs to load all the modules that are required, right? But otherwise, just running the code is really fast in Julia. And you can also try other languages as well. So I will take a break at this point and then continue at 10:15. Okay, so we start with the next part, right? So I put this figure here to show you what are the packages, right, that support shared memory and also the distributed memory. But you remember previously that I said that this shared memory and a distributed memory don't have a clear separation, yes? And sometimes some of these packages can also work with the other type of programming model, right? So for instance, let's say MPI can also have some type of shared memory. It's much more advanced, right? And also distributed can also have part shared memory, yes, but it's also a bit advanced. But here is roughly how you could use the different packages, right, in Python, and what type of architecture and programming model you will be targeting. So let's start with the threads package. And I like this package because one doesn't need to make any further installation, yes, with PIP, for instance, because this is shipped with the base library in Python. This has an issue, however, because it includes a global interpreter log, which tends to serialize the code when using several threads. And because of that, not all the programs, especially the compute expensive programs, are suitable for threads, yes, but starting from the Python version 3.14, this yield is not a problem, right? So, and the threads can run well with Python versions for versions more recent than 3.14. Yes. So this is also something that is not present in our HPC centers, right? And one needs to do some step during the compilation. I try it myself, and it's very nice. Yes, it works, and the threads are not serialized as in the previous versions. So, but here I included an implementation of the 2D integration as I did before. Yes. And here you can see how it works. It uses the threading module in Python. And also here I am parallelizing the 2D integration function. So here I create a workload for each thread manually, right? So then this helps me to define the beginning and the ending for the interval for each thread. Yes. And notice the nomenclature. When we are using the threading library, we refer to the units of work with the threads, right? And here we define the range during the integration, and we are parallelizing only one axis, which is the x-axis in this case. You can also parallelize the other axis as well, but I am just targeting one at this point. And here, each thread will execute one piece of work, right? So here, we are using a shared array, yes, where each thread will save its partial summation. Here we generate the threads. We call the threading function with the arguments similar to the multiprocessing that I mentioned previously. Here we start the threads, join the threads, and report the timing. So for versions of Python less than 3.14, you will see a relatively long time. Yes, but for latest versions, starting from 3.14, as I said before, so you will see a speed up in your calculation. So also in the threaded scheme, we can find the implicit threaded mechanism. And this is already included in linear algebra packages like OpenBlast, LabPack, LKL, right? And these libraries are used implicitly when you are doing the operations, the linear algebra operations with NumPy, for instance. So if you type here numpy.showconfig in your Python script, then you will see more information on the paths and the types of the libraries that you are using in your HPC center. And this can help you to set correctly the number of threads, right? So here there is an example. You can see here, I am simply using NumPy, yes, and initializing a matrix. And then another array called B where I take the dot product of the matrix with itself, right? And then report the time. So you can see here that I am not using any parallelization mechanism, but the parallelization is already done implicitly in NumPy. Yeah. And because of that, I can create this function .py. Yes, it's already here, the same as in this case. And I can run that, yes, by setting the number of threads in my terminal. I will start here with 1. Yeah, and this will use 1 thread. Then I can use here 1 single core because it's 1 thread. Yes. And here I can run this with .py. Also, if you are using a batch script, you will need to export the number of threads in your batch script. Yeah. So you can see that it takes this time, around this time. So if I want to be more precise, I will need to repeat this simulation several times to get to some statistics. And then if I use the 2 threads, I can also set here the value of 2 to be consistent with the number of cores and to not oversubscribe the system. And you could see that, well, the time is less, but it's not that much, but you can repeat it sometimes and see if you get the correct statistics. This is a bit more advanced, yeah. And as you can see here, we are using some implicit mechanism for parallelizing the code, right? So we are not introducing any extra module in Python except for a NumPy. But the situation can be more elaborated if, for instance, if you include some multiprocessing library or threaded library that we saw in the previous example. And at the same time, you try to execute a NumPy linear algebra with several threads. So in that case, you need to be aware of the number of threads and also the number of threads given by OpenMP in this case, and also the number of threads from Python, right? Because these are 2 different things. And because of that, the resources can be oversubscribed easily. Imagine that you request here only 2 threads, 2 cores, sorry, two cores, and here you request 2 threads for OpenMP for the linear algebra operations, but at the same time, you also parallelize these functions in a threaded environment like this one, yes. And here you also use some number of threads. So these threads are not the same. Yes, we need to distinguish this part, right? And because of that, the resources can be oversubscribed easily. Yeah. So this is a more specialized part, yes, and we can include the OpenMP code in our C or Fortran cases, right? We saw the plain Fortran before, but we can also include OpenMP to parallelize our Fortran function, as it is here. Yes, I introduce some parallel directives here for OpenMP. And also we need to recompile the code with additional flag for OpenMP and use this caller, which includes the OpenMP API. Yes. So that's also possible. And finally, execute the OpenMP implementation of the Fortran function. This can also be done with C code as well. This part is also a bit advanced, and here you notice that in the Fortran code, yes, the plain Fortran, I included the parallel directive from OpenMP with a reduction operation. If you know about OpenMP, you will see this that it's a reduction operation collecting the partial summations from each thread, right? But this is still OpenMP in Fortran, right? Plain Fortran code. But currently there is a project, yes, called PyOMP, which offers an interface directly from Python, where you can type your OpenMP code directly without moving to another language like C or Fortran. So here I wrote an example of this function, yes, where we import OMP, and it is included as a number module, as you can see here. So basically, this is the function, integration to D, OMP in this case. And here we define the parallelization. Notice here, this is the parallel directive with the for reduction operation and also including the variable here. So we don't need to move away from Python and use a language like C or Fortran to get OpenMP working with threads, right? So notice that the code was very fast. So instead of using 10,000 here, I am using 100,000, yes, to see the speed up, because it was very fast, yes, for this part. So in this case, you can see that if you run the code with one thread, we have 120 seconds. But if you run it with four threads, it's about 36 seconds. So one see the speed up. And there are several directives and clauses that are currently supported for PyOMP. So, okay, so now I will talk about distributed memory. And we said at the beginning that the difference between the shared memory and the distributed memory is that in shared memory, the cores of the processes or threads, they can share the memory address space, and they can take advantage of the high bandwidth to transfer data back and forth, right? And because of that, your code on a single node using shared memory can be more efficient than a distributed memory code on a single node. But we sometimes also we need to scale our code beyond one node, yes, where the memory is shared, right? And in that case, we need to use another parallelization mechanism, and in this case, we use the distributed memory. So in Python, there is a package called distributed, yes, that you don't need sorry, there is a way to use the distributed memory parallelization. And in Python, there is a module called multiprocessing, right? That is also included in the base installation. And because of that, you don't need to do a further installation with pip install. So how to use that? I return to my previous integration to the function. And here you can see that I am importing multiprocessing. So I don't need to install it in any of our machines, right? And also importing an array, which is a shared array in this case. And here I start the parallelization. Notice that the mechanism for parallelizing is similar in the case of the threading and in the multiprocessing. So the idea is basically the same. We create a workload for each process, and then we define the beginning and the ending of the integration range for each process. And in the terminology for multiprocessing, we call the workers a process or a worker, yes? And in the threaded module, we call it a thread, yes? So here we start the integration, and we are parallelizing as an axis, in this case, only the x-axis, right? So then we collect the partial summations in this part with the partial, for the partial integrals array. And here in the main function, we start the processes. Then we call multiprocessing the process. And here the target is the name of the function, and here are the arguments, yes, in this part. Then we append the processes, start the pool, and then here we wait for the processes until they finish. And finally, we collect the whole integral in this part, yes, and sum the partial integrals values and report the time. So here is how we can run this program. Notice here that I will use four workers or processes, yes, as defined here. And because of that, I need to specify four here, yes. And then execute that, and you see here that the time is somehow reduced, yes. And you can get more statistics if you run that several times. Also within the distributed memory, we can find MPI, which stands for Message Passing Interface, yes. And there is a nice interface between MPI and Python, yes. But you also need to know how to program in MPI previously. So this is the implementation of the previous function. So MPI is implemented in the MPI 4.5 package, and that's why we installed that at the beginning, yes. And here we create the communicator, define the size of the communicator, and get the ranks of the processes. So this is the usual way to work with MPI, where we do the initialization of the environment for the processes. Then here is our function, right? But now with MPI. So the idea is similar to what we have done up to now. We define the workload for each process. And then based on this workload, we define the beginning and the ending of the interval for each process. parallelize the x direction only, and then collect the partial integrals in these variable partial integrals. So then we call the function, yes, and here in this value p, we will get the partial integral for each MPI rank, yes. Notice now the terminology. When we are using MPI, we call the workers, yes, ranks for processes, right? And here, once we have the values for the partial summation, yes, we can use a reduction operation provided by MPI to collect the summation of the partial values of P, yeah? And then report the value of the integral. So here we need to specify on what rank we will do the printing of the values, right? In this case, only the rank equals 0 will print the values. So here, notice how I am running this MPI minus MP4 because it will use only 4 ranks, yes. But for MPI, yes, the srun is not working properly for me on Tetralit. And because of that, it's better to write a script. And the script looks as follows. Yes, an example is here for each center. So you specify the name of the project. So replace these letters with your project name. Then the time. Here is the number of processes that you will use, or the number of ranks, the output error files. This line is not needed except if you need to load Julia for some reason. So then you source the environment that you need. In this case, the environment that we created was this one, yes, and the location of this environment. And finally, you run MPI with MPI run dash NP, the number of processes or ranks, as it's here for Python, and integration MPI.py. So also I found this a package that it's interesting, especially now with the deep learning, yes, workflows. It could help you, yes. And it's called HEAT. So this is a library for distributing tensor operations. And notice here by using MPI as a backend, MPI, the one that we saw in the previous case. Yeah? So he uses a distributed n-dimensional, or they call it DND array. And this can be seen as a global array. But also a local copy of the array is retained, and it contains a chunk of the array, yes? And this one is a PyTorch tensor. For instance, if you run the following example, yes, you load the heat, yes, and then you create an array, yes, a heat array, and then you split that on the direction 0, on the first direction. Then you can print out the type of the array, the shape, and also you can print out the type of the local array that is handled by heat and the shape. yeah, and then you would see that you have two values. One X that is global, right? And then one X that is local, the L array, and that is a PyTorch. And basically, it is doing the splitting, and it can also do the parallelization of the task. So very important, MPI for Pi is used in the background, okay, or as a backend. So here is how one can run the script. Here I have the script already, VIM, hit data types. You can see here it's exactly the same, yeah? And the array has a size of 10 elements. And then here I have a job called job hit, yeah? So this is the project name, the number of ranks that I will use. In this case is 2, because I will split the whole array into 2 parts. Then I will source my environment. This line is not needed at this moment because I don't need Julia. And then I can run it with MPI run. So then I can submit it with SBatch. So the job is running, and let me see. So, and you will see an output similar to this one. So it will print out the size, as it's here. You will see that it prints out the size of the global array, which is 10 elements, and then the local size, yes, of the array, which is 5, and this is a torch array. So it's doing several things behind the scenes, right? So, and you don't need to put the MPI code, as I mentioned previously. Just specify splitting, yes, and then it will distribute the task among the different cores or the ranks. Yeah? So here you can find more information about this package, and here there are some examples that I found. It is for a matrix multiplication. So here you can specify the device where you want to run, either GPU or CPU. And here you distribute the arrays, right? So this is one way to do this. And here, in this case, we split in the direction 0, and we specify the device depending on when CUDA is available or not, yes? And here, this is an efficient way to do the splitting, because in this case, we don't split the second array, yes? So we just split one, otherwise we will create several tasks. And then we just multiply these two matrices. So this is a more elaborated example, and here is for distributing the gradients in a simple model, right? So with heat. And here at the end, I have some words about monitoring the resources usage. We have seen that we can allocate different cores, different nodes in our jobs, and sometimes this allocation is not optimal. So on NAISS, there is a tool called job usage, where you put job usage on the terminal and job ID, and then this gives you a URL, and then here you can monitor the CPU utilization, GPU utilization, the memory, and several other metrics. But in some centers, this tool is not available, and in that case, you can use the commands that I mentioned before, top or htop, to see how the allocated resources are being used, right, in a text-based manner. So here there are two exercises that I wrote. One is for running a parallel code efficiently, and here you will try a different number of processes and also a different number of cores, and here you can detect, yes, if you are exceeding or using the cores in an optimal manner. So I would like this tool to be installed on all the centers, but that's not the case. In Chalmers, this tool is installed as well by default. And here there's an example for an exercise on how to parallelize a for loop. And this is also more advanced, right? Because it involves data frames and so on. But it's also useful and could help you in a more realistic workflow. That's it from my side. Yes, and do you have any questions? You can try the exercise in this last 10 minutes. Yes.